Are you super excited to learn about force and work? They actually are two concepts that seem like they would be very confusing, but they're actually very straightforward, at least the way that we'll teach it. And by will, I mean me, because I'm the one teaching it to you right now. So, I'm just going to start off with the warm-up. We have vector u and vector v, and we want to find the projection of u onto v. So I'm just going to use the formula up here. So the projection of u onto v is going to be the dot product, so that's -6 plus 4 over the magnitude of v squared. So the magnitude of v is 5, so squared is just going to be 25. Almost messed that up. Times vector v, so times -3, 4. All right, so let's simplify this really quickly. So this is really -2 over 25, so I will end up with a +6 over 25 and a -8 over 25. Okay, and in decimal form, that's going to be 0.24 and -0.32. There we go, that's the projection. All right, so the first thing we're going to go over is force, in this very kind of particular situation anyway. All right, so we have someone sitting on a sled on a hill with 45 degrees, and we have someone kind of holding on to that sled right now to make sure that they don't slide down the hill. So the first thing we were given is that the person and the sled weigh 140 pounds. Okay, so that's their weight. And we can actually represent weight as a vector. It's a vector that's pointing straight down towards the center of the Earth, because weight is actually just gravity, and gravity is a vector that's going to connect right down to the center of the Earth. So I can actually draw this right here, okay? And I'm just going to stop anywhere. I don't really know where. I'm just going to stop right there. So I'm going to say this has a magnitude of 140, and it is the actual weight of the person. And what we're being asked to find is what's the force required to prevent them from sliding down the hill. Okay, so basically how much force does this person have to hold on to the sled in order to prevent them from going down? So what's kind of neat about this is that force that we're trying to figure out, it's actually the vector projection of the weight onto the side of the hill. So I can basically drop this perpendicular, because remember projections drop down to form perpendiculars, and this right here is the vector that is representing the amount of force that's required to keep them from going down the hill. So that would mean that the person is pulling that way, so the arrowhead would be going that way, whereas this person has a force that's trying to go that way. So if we have one force going this way and one force going that way, they cancel each other out, and that's why the sled doesn't move. Okay, so the sled wants to go this way, and we have someone holding it that way. And that's what we're trying to find, this force right there. Okay? So now we have this basic idea down. What I'm going to do is extend some of these lines so we can see what's really happening here. So if I extend this line and extend this line, these form a right angle. So that means that this angle right here, this one right here, and this one way up here, which I'm just going to call fish or alpha, that they are in a 90-degree right triangle. Now, if I look at the triangle that's formed with the black, blue, and this dotted one, they are also in a 90-degree triangle. And I know that this one now has to be 45. It has to line up with what this one was, because I had 90, 45 plus fish. So in this little one, I have 90 fish. This one has to be 45. So I know that this angle right here is always identical to that angle right there in this setup, even if I don't actually show any work whatsoever for it. And then I don't need my little fish guy there. So in that little triangle, we can see opposite and hypotenuse. So sine of 45 degrees will equal the force over that weight, or 140. So the force required for this person to prevent this one from going down the hill is going to be 140 times sine 45. And we all know, I'm sure by now, that sine 45 is the square root of 2 over 2. So I can just multiply this out, and I get 70 square roots of 2. And it's in the same exact units that our weight was, so pounds. And this is approximately 98.9949 if we use the calculator. So this is how many pounds of force are required for this person to prevent that one from sliding down the hill. So to summarize this situation here, whenever we're asked about force and weight, we always have this kind of same exact situation where we have this kind of weird Nike upside down check mark. We drop a line straight down, okay, and then connect it up to form a right angle right there. This angle's always equal to that angle. This is always the force, and this is always the weight due to gravity. And so we can always write that sine theta will equal the force over that weight. For example 2, we have a force of 30 pounds just keeps a box from sliding down the ramp, inclined at 20 degrees. We want to find the weight of that box. So this is a little bit different. This time we're going to be finding the weight. We were given the force. So even though it gave us a picture there, that picture is pretty much the worst picture in the world. So I'm just going to redraw it. And I'm just doing that same shape that we do every time. And if the incline is 20, then both of those are 20. We know that the force required to keep some box that's up here on the side of the hill is 30 pounds, okay? And I want to find what this weight value would be right there. So I get sine of 20 is going to equal the opposite over the hypotenuse. I'll do a little flipperoo there. Really official math term right there. So I get that this box actually weighs 87.71 pounds. Example 3 looks like it should be very, very confusing, but it's actually very easy because they gave us a lot of information. So what I'm going to do is kind of describe the situation and what's going on, and then we'll answer it, and you'll see that it actually is super easy. But start off with, we have this box that's on some sort of incline here. So I'm going to draw a little box right here. Here's my box. And it is on an 18-degree incline. Now, someone is either holding this box or pushing this box or doing something with the box, and they're forming a different angle with it. Okay, so here's some person doing something with it. That's a great stick figure. Let's make it me with spiky hair. I didn't do my hair today, so. And I did just shed all over the board. Woo. All right. So that person, they form a 25-degree angle to the side of this incline. And that's actually why they've made this so easy for us, is they gave us this information here. A lot of times what they would do is actually give us what this red angle is to the horizontal, which I think would be 43. And we would have to actually calculate it. And they also wouldn't specifically give us any other angles. They would give us this in vectors and say, like, this red thing has a vector, and we would have to find the direction angle, which is super annoying. But here's this setup. Now, this person's pulling this way, and they're pulling the box up the side of the hill here, okay? So they're moving it this way, but they're pulling it this way. Do we get how those are in different directions? And this is where the projection comes into play in real life. So the projection is the effective force in a direction. So if we're pulling it this way, but it's moving this way, then this is that effective force. Okay? It's what is actually being transferred in this direction. Even though we're pulling in another direction, we're putting a little bit in this direction. So if we were actually in school and I could actually like show you what was happening here, the example I would do is take one of you sitting in your little desks, okay? So here's one of your little desks. It's beautiful, isn't it? And I would stand directly in front of it, and what I would try to do is pull it towards me, but I would make sure that the way my arms were angled is that I was actually kind of pulling this way on it, okay? So if this is the eraser, is the desk, my arm is at an angle to it, and I'm trying to pull it sideways, okay? And I probably wouldn't be able to move the person in that desk. Now, if I took that same situation and then maybe crouched myself down so I got a little bit lower, and then I pulled it towards me this way so that the way that I'm pulling it is lined up directly with the direction I'm pulling it in. So that would be like if I went like this and pulled it towards me, it's significantly easier than if I'm at an angle trying to pull it towards me. And that's because more of the effective force would be lining up with the actual force that I'm doing. So this is the force that I'm exerting, and I'm only exerting a certain amount in a given direction. And that's what we got going on here. And that was a very long-winded way for us to say that this question is super easy, because they asked us for the effective force, which is this value right here, and this forms a giant right triangle. So I have cosine of 25 equals that effective force over that force right there. But they told us that this is 60 pounds. So all I have to do to find this effective force, which is really the length of the projection of the force onto some surface, is just going to be equal to 60 cosine 25. And I'll just literally type this right in the calculator, and I get 54.37 pounds. So that's how much force is actually being exerted in the direction I'm pulling this box. So of the 60 pounds, only 54 of it is going this way. The remaining 6 is actually going vertically, and that's where this 60 comes into play. Okay, so 54 of it is sliding up the hill. There's 6 point whatever is actually going vertical, so that's being lost in terms of the movement that I'm trying to do here, because I'm actually applying 60. So whole lot of words in that problem to basically just ask you to draw this triangle and solve for that side length. And if we're looking at what I ended up here, this effective force is the length of the projection is 60 cosine 25, and that's the alternate formula that I mentioned in the previous video for the length of the projection, force cosine theta, 60 cosine 25, where 60 is the force in the direction, okay, and 25 is the angle in between the direction and the way that we're moving things. And that's what we're going to use when we transition to work. For work, there's a whole bunch of words here, and honestly, we're going to ignore most of them, all right? The work is the amount of energy that it takes in order to move something. And what we do to figure that out is we take the effective force we're moving in a direction and we just multiply it by however far we're actually moving it. So work is equal to essentially the effective force, so the length of the projection times some distance that we're moving it by. And rather than using this formula, I'm going to use F cosine theta. So work equals force cosine theta times the distance, okay, where this is going to be the force in a given direction. This is the angle in between the force and the way that we're going, okay? So if I am pulling something this way, but I want to move it that way, so this is the direction I'm moving, and this is the force, and this is theta, okay? And then this is basically how far I'm moving it. So, I mean, it's distance. Do I need to really label it more than that? So we have to memorize this. Work equals force cosine times distance. So we have 3 different examples to work with using this force cosine theta times distance. So the first one is the easiest. If we have a work done by 10-pound force acting in the direction of 1, 2, moving an object 3 feet. Okay, so we have to remember we're trying to find work, which is force cosine theta times the distance. Okay? And they told us that we have a 10-pound force, and they told us that we're moving it 3 feet. So the only thing that we actually need to do here is figure out what is this cosine theta value, okay? And that's actually super easy to do because we just need to find the angle between the force of 10 and the distance that we're traveling. So they told us that the force is going in the direction of 1, 2, and then they said that we're moving horizontal. So what I'm going to do is grab the horizontal unit vector, which means that I'm moving in the horizontal direction and not in the vertical at all. So here's 2 vectors. The first one represents the direction of the force. The second one represents the direction that we're moving this object in. And all I need to do is find the angle in between them using the angle in between formula that we have that I was going to point at. I don't have it over there, but we should hopefully know it by now. It is that cosine theta equals the dot product, so 1 times 1 plus 2 times 0, over the magnitude, so that's square root of 5, times 1. That's why I bothered to use the unit vector for the horizontal direction, because its length would be 1, super easy to work with. All right, so this is going to be 1 plus 0. So I get that the work is equal to 10 times 1 over the square root of 5 times 3. Or 30 over the square root of 5, which is approximately 13.42. And then we have the greatest unit of all time. So force was in pounds, distances was in feet, so we end up with this lovely unit called foot-pounds, which your science teachers would hate that we use. They use like maybe newtons or joules or something. I don't know. I'm not a physics person, so some of you are screaming it at your computer right now saying like it's newtons, whatever it is. I don't know. That's the answer. Done. So it boiled down to us needing to figure out what cosine theta was. Example 2 is just a little bit trickier because this time they didn't quite give us wonderful vectors to work with, but we have the work is equal to force cosine theta times distance. It's always the same. They told us the force was 50. We don't know what the angle in between it is, and they said we're moving it 5 feet. So again, we just need to find cosine theta, and we'll use the angle in between formula. They told us the force is at 2, 3. This time they said we're moving it along the line y equals x. So what I need to do is turn this back into a vector. So the way I do that is using slope. So I have y over x, which turns into 1, 1. So that's going to be the vector I'm going to use in order to do the angle in between. So I get that 50 times the dot product, so 2 times 1 plus 3 times 1 over the length of this, which pretty sure is 13, square root of 13, and this is the square root of 2, and then times 5. So to simplify here, I get 2 plus 3, so that's 5 over the square root of 26 times 5 times 50. And if I do a whole bunch of fun-filled math here, I'm going to get 1250 over the square root of 26, which is approximately 245.15 with our favorite new unit, foot-pounds. For example 3, they give us a 80-pound force acting in the direction of AB, okay, which is equal to 4I plus 5J, which remember is just 4 comma 5, so we don't really need to think about that too much. And they actually tell us the angle in between is 60 degrees, so they did some of the hard stuff for us. So let's see, work is equal to force cosine theta times distance. So force is 80, they gave us that. They gave us the angle in between, 60. So what we don't know is the distance. And they said that we're moving from A to B. And just so happens that the way this is denoted here, vector AB, that if we just find the magnitude of this vector, that is going to be the distance then that we're traveling. So do 4 squared plus 5 squared, and the square root of that, I'm pretty sure is the square root of 41. So I just multiply by the square root of 41. Cosine of 60, I'm sure you all know, is 1/2. So I get 40 times the square root of 41, which is approximately 256.125. Favorite unit, foot-pounds. Yay, math. Congratulations. You now know how to deal with basic force and weight problems as well as work problems. So the rest of the packet is practice, and there's some additional practice on the last 2 pages of this packet that you're not required to do. It's just kind of some sort of mixed review that's going on there that I basically had a bunch of extra questions and I just threw them in there so that you had them. Yay! You're done learning everything for this chapter. That's everything there is to know about vectors that we're going to cover. So hopefully you think that they are super fun and easy, because they can be. Can you see? I don't know which way I need to face that. I might be rambling on now. Should I cut this or just leave it in there for you?